Okay, inverse trigonometric functions. Inverse functions in general switch x and y values. In other words, they undo each other. And to see that, let's take an example from algebra. Here's our original function f of x equals 2x minus 1. So if I write that as y equals 2x minus 1, and I switch x and y and solve for y, I will end up with the inverse of f. And so we can say that f inverse of x is x plus 1 over 2. So let's see what's going on here. Here in the original function, x is being multiplied by 2, and then we subtract 1. The inverse function takes x, adds 1 to it, and then divides the whole thing by 2. So we're doing inverse operations, addition instead of subtraction, division instead of multiplication, and we're doing them in the opposite order. A function has an inverse if it passes a horizontal line test. For example, y equals x squared does not have an inverse because y equals x squared does pass the vertical line test, right? A vertical line only intercepts it in one place. But if I did the inverse where I switched x and y, it would look like this. Okay, and the inverse does not pass the vertical line test. So without having to graph the inverse function, we just say, well, if the original function doesn't pass the horizontal line test, then the inverse will not pass a vertical line test, so it does not have an inverse. So what about trig functions? Well, you may remember that the graph of sine definitely does not pass the horizontal line test. It's going to intersect an infinite number of times practically anywhere we want. So what we do is we artificially cut off sine. Okay? So we say, okay, we're only going to look at sine between negative pi over 2 and positive pi over 2, which is this bit right here. And now if all I look at is that bit right there, it will pass the horizontal line test. And you're saying, well, what about all these missing parts? Well, the cool thing about trig functions is that they just repeat themselves over and over again between 1 and negative 1. So to get every possible value in the range of sine, all we need to do is look at sine between negative pi over 2 and positive pi over 2. And if we go ahead and graph that, whoop, I'm in the drawing mode, sorry. If we look at that, there you go. You can see now, here's the graph of arc sine or inverse sine of x. It has a domain between negative 1 and positive 1, and the range goes between pi over 2 and negative pi over 2. Okay, so to summarize what we're talking about with sine and arc sine, we say that the inverse sine function is defined by y equals arc sine of x if and only if sine of y equals x, where the domain of x is between negative 1 and 1, and the range of y is between negative pi over 2 and positive pi over 2. Okay, in plain English, what does that mean? It means if you're talking about arc sine of x, you can only get answers between negative pi over 2 and positive pi over 2. As far as the inverse sine function is concerned, the second and third quadrants do not even exist. Okay, so now let's do some examples. What is the arc sine of negative 1/2? Well, you have to ask yourself, on the unit circle, within this range here, where does sine equal negative 1/2? And that is at negative pi over 6, not 11 pi over 6. Negative pi over 6. Okay? Alright. Let's do this. Where does sine equal root 3 over 2? Positive root 3 over 2. That is right here at pi over 3. Okay, how about the inverse sine of 2? Well, this does not exist, because there is no value of theta whose sign equals a number greater than 1 or less than -1. So 2 is outside of our domain for arc sine or inverse sine, so this answer does not exist. Okay, so how about inverse cosine? Well, with inverse cosine, when we graph cosine, once again it does not pass the horizontal line test, but now we're going to limit it to only values of cosine between 0 and pi. Once again, that picks up all of the y values we need from 1 to -1 if we just limit our domain to 0 and pi, which means that our arc cosine will have a range from 0 to pi and a domain from -1 to 1. So to summarize, if y equals the arc cosine of x, x is between -1 and +1, and y is between 0 and pi. Practically speaking, that means that if you're dealing with inverse cosine, you can only get answers in the first and second quadrants. As far as arc cosine is concerned, the third and fourth quadrants do not exist. Okay, let's talk about the inverse tangent function now. So here you can see the red is regular tangent, which obviously fails the horizontal line test. And so we limit our tangent function to only go between -pi/2 and pi/2. So we're only going to look at this central part of tangent. When we do the arc tangent, it now becomes this, and we have horizontal asymptotes instead of vertical ones, going -pi/2 to +pi/2. So if y equals the inverse tangent of x, then that means that x is going to be between -infinity to infinity. In other words, all real numbers. See that blue? It goes forever to the right and forever to the left. And y is going to be between pi/2 and -pi/2. Not equal to, but between. I said equal to, and I shouldn't have done that, right? Okay, there. Okay, so practically speaking, that means that the answers you're going to get from arctan are going to be the same as the answers you get from arcsine. Only angles between 0 and +pi/2 and 0 and -pi/2. Okay, so let's do some examples. What is the tangent of the arctan of -3? So this is saying what angle has a tangent equal to -3. And so we're going to take the tangent of the angle whose tangent is -3, and the tangent and the arctan cancel each other out, and the answer is -3. Okay, how about the arc sine of the sine of 5pi/3? Now we need to be careful here. Let's work from the inside out, okay? So we're going to do the arc sine of the sine of 5pi/3. Okay, from the unit circle, 5pi/3 is in the fourth quadrant, so it's negative, and it's a pi/3, so it's -√3/2. The arc sine of -√3/2, since it's negative, is going to be a negative first quadrant answer, so that will equal -pi/3. Tangent of the arc cosine of 2/3. Okay, here I think it'll help if we draw a triangle. Since we're doing the arc cosine of a positive number, we are in the first quadrant, and cosine is adjacent over hypotenuse, and by the Pythagorean theorem, that's going to be 9 minus 4 under a square root, so we get the square root of 5. Okay, so now we can find the tangent of this angle. The tangent of the angle whose cosine is 2/3 is equal to opposite over adjacent root 5 over 2. Okay, so how about a problem like this? The arc cosine of 0.37. Now that's not an angle that from the unit circle that we've memorized. So we're going to use our calculator, and all of your inverse functions are up above your normal functions. So I'm going to go second cosine 0.37, and your calculator will automatically give you the correct answer, 1.192. That is in radians. If you want it in degrees, you need to change your mode. So I'm going to arrow over to degrees, hit enter, quit. Now I'll do second entry, and we'll get the answer in degrees, 68.28 degrees. And one last example. We're going to use an inverse trig function to write this angle theta as a function of x. Well, you'll notice that the pieces of the triangle we have to work with are the opposite side and the adjacent side. So that means that the tangent of theta is x plus 2 over 8. Okay, if that's the tangent of theta, then that means that the arc tangent of x plus 2 over 8 equals theta. And that's our answer. We've written theta as a function of x.